Hello everyone, welcome back. So in this section, we will talk about, we will study integration strategies. In the previous sections, we introduced various methods for evaluating integral, but always in the context of learning a specific technique of integration. In this section, the chief goal is to illustrate how to attack a generic integration problem when the appropriate method is not obvious. So, as a starting point, we assume the integral list, that the basic integral formula I gave it to you, that you know that, and that you are familiar with the reduction of formulas presented in the previous section as well, like in section 8.2 and 8.3. So let's start with the first problem, evaluating the following integral. You can see to evaluate the following integral, we have to rewrite the integrand because we don't have a basic formula or anything like that, right? So if I'm asked to solve this one, what am I going to do is, I'm solving the integral of science x plus 1 divided by cosine square of x dx. I can rewrite this one as 1 divided by cosine of x, right? Times sine x divided by cosine x plus, let me put this inside one bracket, plus 1 divided by cosine square x, right? Because if you look at this one, if I multiply, this is multiply 1 times sine x is sine x, cosine x times cosine x is cosine square x, and then plus this 1 divided by cosine square x. Why am I doing this one? So I can see I will have 1 over cosine x is what? Secant x, right? Sine x divided by cosine x is what? Tangent x, right? Dx, I can separate these two to two integral, plus 1 divided by cosine square is what? Secant square x dx. Does that make sense to you? And then after this one, we can use the table of integration, right? The integration formula to integrate both integral easily, right? So you can see I use what my knowledge in trigonometric to rewrite this integral so I can use the formula that I have, which you can see this one will be what? Secant x times tangent x dx, like your a is 1, so it will just be secant x plus c, sorry, not plus c, because I have to integral. So I have to find the second one first. Then plus, and the antiderivative of secant square is what? Tangent x. So tangent x plus c. And that's it. Right? That's it. So that's one thing we have to do. And also, if I'm asked to find the integral of, evaluate the integral of x squared divided by square root of 4 minus x to the power of 6. So in this case, I have to think about substitution, because what I have on my denominator is like a square minus u square, basically. So to do this substitution, first thing, you can see the denominator of the integrand, which is what? 4 minus x to the power of 6 can be written as x to the power of 3 square, right? Looks promising, particularly because a constant multiple of the derivative of x cubed appear in the numerator as well, because the derivative of x cubed is what? Like 3x squared. We know that. So because of that, therefore we try to make our u substitution. We'll say let u be equal to x to the power of 3. Then if u is x to the power of 3, what will become my du? Our du will be 3 times x squared dx. Or you can see we do have x squared dx in the numerator, right? So I can, we don't have 3, so which means 1/3 du, that's what will give me x squared dx. That's what appears in the numerator, x squared dx. So therefore, we can write what? Our integral of x squared divided by square root of 4 minus x cubed dx is equal to x squared divided by square root of 4 minus x cubed square, and using our u substitution, we can say what this is 1/3, because 1/3 is a constant that can go out, du, because my du will be what? 1/3 du is x squared dx. I took 1/3 out, so it will be du divided by square root of 4 minus u squared. And du divided by 4 minus u squared can be found in the table, right? You can find that in the table, which is like what? Sines inverse of x, right? And then what is our a? Our a is 2, because we have 4 here. 2 squared is 4. So basically, this will be like this 1/3 sines inverse of a is 2, so u divided by 2 plus c. What is our u? Since the beginning is x cubed, so I would just say my final answer would be 1/3 sines inverse of x cubed divided by 2 plus c. And that's it. Okay. So now next, we are asked to suggest a technique of integration for each of the following integral based on the pattern of the integrand. So in this case, I'm not going to solve them, okay? I'm just going to give a technique, suggest a technique for each of them. So let's look. Again, this is not like by looking at it, you cannot say, okay, I would use this one. Sometimes you can start a method that does not work, and then by doing that, you will think, okay, maybe I can do another method, and so on. But anyway, it's always good to start from somewhere, right? So first thing for A, one thing I will do first is I'm going to distribute my x in the denominator. So to see what I will get. So I know the integral 4 minus 3x squared divided by x times x squared minus 4x minus 4, sorry, not 4x, dx. If I distribute the x in the denominator, I will get what? 4 minus 3x squared divided by x cubed minus 4x. And of course, dx, if I let my u be equal to x cubed minus 4x, then my du will be what? 3x squared minus 4 dx, right? Of course, that's not exactly the same thing we have on the numerator because the numerator is 4 minus 3x squared, but they look the same, right? So which means if I multiply my du by negative, then my negative du would be exactly what? 4 minus 3x squared dx, because you multiply the right side also by negative, so you will have a negative, which is my numerator. So you can see this substitution lead us to what? This substitution lead us to, if I do my substitution, I will have what? Negative, because this negative, we can take it out. That's a constant, du over just u, which is a standard integral. And I know you know, which is what? Just ln absolute value of u plus c. What is your u? You substitute your u. That's it, right? If you have question, please stop the video and do it again. So for B, we can see the integrand suggests several techniques, right? The substitution u, we can substitute u to be 1 plus x squared looks promising, given du will be 2x. That appear in the integrand, right? This choice led us to what? But if we do that, like if we said let u be equal to 1 plus x squared, and then du will be 2x dx, right? We have x dx right here. But if we do that, which means 1/2 du will be equal to x dx, because we have x dx. So in that case, if I do that, I will get a problem that is even more difficult to find, because look, in that case, my x integral of x e to the power of square root of 1 plus x squared dx would be 1/2 integral of e square root of u du, right? Which require a Crafty substitution followed by integration by parts. So this will take long, right? That's difficult to evaluate, right? So we will not do that. So we have to think about another strategy again. So given that the integrand is a product of two functions, we might try integration by part as a first step. Okay. So I was saying, if I try to do integration by part, like this, that also will be hard. Why? Because you know, e to the power of square root of 1 plus x squared, if I make that my u, my du will still be, I will still have to do integration by part again. So finally, the presence in the integrand suggests a substitution, 1 plus x squared. This suggests a substitution because I want to get rid of my square root. So what I will just said, since this does not work, let me have a line to separate. What I would just said, let x be equal to tangent theta. Why? Because I will have 1 plus tangent square theta, and square root 1 plus tangent square theta is an identity, trigonometric identity, which is what? Second square theta. So that will cancel with the square root, because what is making this hard is the square root. So I have to think about get rid of my square root. Then if x is tangent theta, then my dx would be the derivative of tangent theta is second square theta d theta, right? So let's rewrite. I will get the integral of x times e to the power of square root of 1 plus x squared dx will be now, what is our x? We said tangent theta. Doing the substitution, so we will have tangent theta e to the power of 1 plus tangent square theta, and dx is what? Second square theta d theta times second square theta d theta, right? So now if we rewrite the integral to prepare for substitution again, of course, 1 plus tangent square theta is what? Second square theta, and square root of second square theta would be second theta. So I will have, I'm going to write, because this is second square theta, right? I'm going to, or let me simplify this one first. E integral of e to the power of second theta. Why? Because if this one is, this is second square theta, okay? And square root will cancel out. So times tangent theta second square theta d theta, right? So I'm going to rewrite this one. So I will use again another substitution. How do I rewrite this one? Because this is second square theta, I'm going to write as second theta, the integral of second theta times e to the power of second theta times second theta tangent theta. So I break down second square theta d theta. So now the substitution that I would use will be, now I will just say let u be equal to second theta. Then our du will be what? Second theta tangent theta d theta, right? So by doing this substitution, so you will see now our integral will be u e to the power of u du. Does that make sense to everyone? You see how beautiful this is? And then you can do what? Integration by part to integrate this one now. Okay? I will let you do the rest. And then use integration by part. Okay? Last but not okay, I have two more. If I'm asked to evaluate the integral of ln of 1 plus x squared dx. So if we look at this one, of course, we have integral of ln of 1 plus x squared dx. The 1 plus x squared dx is present in the integrand, so we could try substitution x is equal to tangent theta again. But again, we will have to do integration by part. But if you look at this one, since the beginning, we can use integration by part. We have 1 times ln of 1 plus x squared, right? We just said u is ln of 1 plus x squared, which means du will be what? 2x divided by 1 plus x squared dx. And then dv would be 1 dx, right? So which means v would be equal to x. So if I do that, my integral, sorry, I lost my code. So the integral of ln of 1 plus x squared dx will be what? It will be u times v. So we'll have x ln of 1 plus x squared minus v du. So we have a 2 right here. We can take these 2 out. Or let me write 2x squared divided by 1 plus x squared dx. So if you look at this one, 2x squared divided by 1 plus x squared can be handled by doing what? Long division. We have to break this one down into 2 fractions first. And then the second one, you will see you can use a table of integration to find it. Because if you look at your table of integration, we have tangent inverse is what? Dx over 1 plus x squared. So once you do long division, divide 2x squared divided by 1 plus x squared, you will be able to solve the rest. Okay? Since it's the question just asked to use which technique, okay? And now we are asked to evaluate x times square root of x. So x times square root of, I mean x times e to the power of square root of x. Should I let you do this and stop this video? Because we have practiced few of them already. So in this case, I will just set let u be equal to square root of x. So if u is square root of x, then x will be what? U square, right? Which means dx also will be what? 2u du. So if I do my substitution again, you can see the integral of xe to the power of square root of x dx would just be, we have a 2 the integral of u, we have x is what? U squared. So u squared times u will be u to the power of 3 e to the power of u du. Right? And then to find this solution, you have to do repeated integration by parts. So you have to do integration by part. How? Because you can see this is power 3. So if you make it your u, the derivative will be 3u squared. You will still have to do, it will be 6u. You still have, so you have to do 3 integration by part to solve this one. So that's what you need to know in this section. I will see you in the next one.